All right, let's dive right into this explainer. Today, we're going to demystify the complex math of classical mechanics to reveal the unbreakable rules of our universe. Whether you're analyzing a simple pendulum swinging back and forth or the insane orbital mechanics of distant galaxies, the underlying mathematics rely on a few profound principles that simply never cheat. Basically, we're going to read the universe's own source code. Here is our roadmap for today. We'll start with constants of the universe, then move into conserving linear momentum and conserving angular momentum. After that, we'll tackle the conservation of energy, and finally, we'll wrap up with the secret ingredient, symmetry. Constants of the universe, finding what stays the same. Think about it for a second. We live in a universe of constant, chaotic motion. Planets are spinning, particles are smashing into each other, and objects are perpetually falling, pushing, and pulling. To actually make sense of all this absolute chaos, we have to find the hidden properties that never alter. We really need a mathematical bedrock. So what are we looking for? Well, it's called a conserved quantity. Basically, when the derivative of a property over time, that's dq over dt, equals exactly 0, it means that no matter how much time passes or how much things move around, that specific value absolutely refuses to budge. It's nature's ultimate cheat code. Conserving linear momentum, the power of no push. Now, take a look at the math here. Equation 1.14 shows us that when force is 0, the derivative of momentum with respect to time is also 0. And remember, this is a vector equation, right? That means if even one directional component of force is 0, let's say the force along the x-axis, then the momentum in that specific direction is perfectly conserved. It is locked in. To translate that calculus into plain English, it just means this: if absolutely nothing pushes or pulls an object, its momentum stays exactly the same. And yeah, you probably recognize that. It ties perfectly into Newton's first law of uniform motion. The universe is essentially dictating that an object coasting through the void is going to maintain its momentum for eternity, completely unaltered, unless some new force interrupts it. Conserving angular momentum, the power of no twist. Okay, let's take this idea into rotational mechanics. Here, we replace force with torque, which is basically a twisting force. Equation 1.15 shows us that when torque is 0, dl over dt equals 0. So L, which represents angular momentum, has to be constant. But the text points out something super fascinating here. Torque is the cross product of the position vector and force. So it's 0 not just when there's no force, but also when the force is strictly parallel to the position vector. Think of gravity pulling a planet directly toward a star. And this brilliantly illustrates our second rule. If you don't twist an object, its rotational momentum is totally conserved, locking its spin right in place. Honestly, this is exactly why the Earth keeps spinning on its axis day after day. And it's why an ice skater spins way faster when they pull their arms in. The total angular momentum is mathematically locked. The conservation of energy, the work-energy balance. Now let's talk about energy. The work-energy theorem proves through line integrals that the work done by a net external force perfectly equals the change in a body's kinetic energy. If you're moving from point A to point B, the integral of force over a tiny displacement perfectly balances out to the final kinetic energy minus the initial kinetic energy. It is like this beautiful mathematical ledger where every single joule of work is strictly accounted for in the speed and mass of the object. No miss in change. Next, the text introduces the concept of a conservative force, kind of like gravity. With a conservative force, the work done only depends on your starting and ending points, completely ignoring whatever wandering, winding path you took to get there. Whether you drop a bowling ball straight down or let it roll down a crazy spiral ramp, the work done by gravity from the top to the bottom is identical. And here's the really wild part. If you take a closed path and end up exactly where you started, the net work done by a conservative force is absolute 0. Because of these conservative forces, the math brings us to such an elegant conclusion. The total mechanical energy, which is kinetic energy T plus potential energy V, is a constant of motion. As a particle falls, sure, it loses potential energy, but it gains the exact same amount of kinetic energy. The total sum, E, it just refuses to change. So let's take a breath and summarize these 3 superpowers we've just decoded. First, if total force is 0, linear momentum is conserved. Second, if total torque is 0, angular momentum is conserved. And third, if forces are conservative, total mechanical energy is conserved.
It's basically a trio of unbreakable rules that governs everything from an apple falling from a tree to entire galaxies colliding. The secret ingredient: symmetry.
All right, what if I told you that momentum and energy don't just conserve themselves by magic? They are actually dictated by the fundamental symmetries of the universe itself. Now, symmetry in physics isn't just about shapes looking identical in a mirror. It means the actual laws of reality do not change if you shift your experiment through space or delay it through time. In fact, the very last paragraph of our source material drops this massive theoretical concept on us, connecting all these dry equations we've been looking at to the actual design of reality. It hints that determining a priori conserved quantities is one of the single most useful tools we have for understanding mechanical systems. And the deepest root of that tool? It lies entirely in symmetry. There's a quote by theoretical physicist Robert L. Mills that goes, "For every conservation law, there is a symmetry." And wow, that perfectly captures the grand reveal here. The math we just translated isn't just about moving objects. It's a reflection of the perfect symmetrical balance woven right into space and time. Conservation of energy exists literally because the laws of physics are symmetric through time. They don't change from today to tomorrow. Linear momentum is conserved because physics is symmetric through space. A meter over here is exactly the same as a meter over there. So, as we wrap up this explainer, I want you to look at the world around you a little differently. If fundamental symmetries dictate the unbreakable rules of our reality, what incredible symmetries are we yet to discover? What other cheat codes are sitting right in front of us, encoded in the math, just waiting to be uncovered? Keep looking for the constants, guys, and you just might find the hidden architecture of reality itself.